Hey everyone, welcome back to the MetaLogic podcast. I'm your host, Aditya, and today we have Ryan here, and we're going to be discussing an introduction into machine learning and what machine learning is.
Hi, Adi. Thank you for having me. I'm pretty excited to see what we would be discussing about today because I think it's pretty interesting and it's a pretty relevant topic in today's data consulting world and data science world and just the business world in general.
Yeah, and if you're listening to this, we're assuming that you're already interested in data science and machine learning. So we're going to go into the details about a specific algorithm in machine learning and talk about the applications of the future. Before we get into machine learning and data science, I think it's important to take a step back into predictive analytics. But really, to dive into predictive analytics, we needed to take a step back behind that into how most companies right now are making decisions for their future. And a lot of the decisions being made right now are through Excel documents. It's through really looking at spreadsheets, looking sometimes at visualizations and dashboards, but it's really human-driven decision-making right now. But some companies are moving into, what predictive analytics are. Ryan, if you want to talk about predictive analytics.
Yeah, so predictive analytics is essentially, as the term itself suggests, making some sort of predictions, right? So what data scientists have started doing probably a decade or two ago is coming up with these algorithms. Actually, the algorithms always existed. We just got the necessary compute to sort of process these algorithms. But essentially, data scientists came up with algorithms such as very well-known linear regressions, logistic regressions, naive Bayes, K nearest neighbors, and there's so many of them out there. They took these algorithms, they took data sets from the company's warehouse. They then put the data set to the algorithms and made some sorts of predictions on it. But the key here is, and this does not apply to machine learning, but more so applies specifically to traditional predictive analytics, is that these algorithms are very rule-based. So they're explicitly coded using if-then statements and very simple coding languages, although the algorithms themselves could be complicated. But then these fairly simple algorithms do perform well. They're not bad by any means. But this sort of transitioned into what we call at MetaLogic supervised machine learning algorithms. And you may want to talk about it a bit, Adi.
Yeah, but before we go into that, you said the word supervised, right? So what's the difference between supervised and unsupervised?
So supervised is when you have an outcome defined, when you have a target variable, when you know exactly what you want to predict. I want to predict the price of an Uber car. That's a supervised model. So an unsupervised model is more when you want to figure out random patterns in the data, when you want to describe the data, but you don't have one specific target variable as an outcome.
Is it fair to say that machine learning really delves into the unsupervised portion?
It delves into both. So we'll get into it in more detail in a few minutes, but you do have unsupervised machine learning. You have text mining, you have social network analysis, you have recommender systems, you have clustering systems within machine learning. But the most of what we're going to talk about today is supervised machine learning. And we probably will make another podcast on unsupervised.
So machine learning is basically taking predictive analytics a step further, right?
Exactly.
It's basically, instead of if-then statements, instead of rule-based algorithms, it's now the computer and the machine learning algorithm understanding complex and nuanced relationships in the data and making their own predictions. So now you're no longer, defining what you want to look for.
Exactly.
You're just saying, hey, this is the data, go find me something.
Yeah, and there's obviously that there are some criteria. There is a structure to this madness too. It's not just a crazy algorithm that goes out there and does its work or does its magic.
Yeah.
It has some logic to it. But this logic has the freedom to act on its own. And I think it'd be better if you get into an example.
So let's look at the random forest, right?
Yeah.
Random forest, you said that it's maybe the simplest one to understand.
Yeah, so I think random forest is a really good example because it has almost an equivalent in the predictive analytics realm. So let's look at CART, classification and regression trees. Now, CART is one of the most sophisticated algorithms in the predictive analytics realm. And actually, to understand CART versus random forest, let's introduce a pretty simple example. So let's say you're Uber and you're trying to predict an outcome, and that outcome is the price of your cabs. And to predict this outcome, you're using sort of input variables. You're using distance, the source location, the destination location, surge multiplier, the demand, the weather variables, and so forth to predict price. Okay. So what CART does is essentially it creates a decision tree based on the splitting of the input space. And this could be multi-dimensional or two-dimensional depending on your data set. In this case, multi-dimensional. Okay, and we can get into this more specifically if you want.
So before you really dive into here, can you give just like a basic understanding of what a decision tree is? Because that's something that we know, but maybe it's not so apparent, right? What is a decision tree?
Okay, so let's say we have the trained cart model. Okay, and this cart model essentially has a root at the top, and it based on decisions based on certain criteria, it either goes left or right. Okay, so let's say, okay, let me give you an example. The first root of the decision tree could be, was the distance of the cab greater than or lesser than 4 miles? If it's greater than 4, it would go to the right. If it's lesser than 4, it would go to the left. Okay, and then let's say it's greater than 4, so it goes to the right. It then goes through another decision criteria. Was the source location within Back Bay South Station of Boston? Yes or no? If it's a yes, it might go one direction, and no, it might go another direction, and so forth until it reaches the bottom of the tree. At the bottom of the tree, there lies a prediction. So
Mm-hmm.
essentially, every record or every observation that you put in at the top of the tree, based on decisions, makes its way to the bottom of the tree where it gets its prediction. Okay, so that's kind of how CART works. The trees themselves are built in a very fascinating way. So there's this thing called deviance, okay, or impurity. So what the algorithm is trying to do is it's trying to draw lines or planes in the multi-dimensional space in such a way that it. Let's take a classification example. It's easier to understand. Let's say we're trying to predict expensive cabs and cheap cabs, not a price per se. Okay, so it's trying to draw lines in or planes in the multi-dimensional space such that all the expensive cabs are split to one side and all the non-expensive cabs or the cheap cabs are split to the other side. So essentially, it tries drawing lines for every single variable and every single value of that variable, and essentially it sees which variable value combination reduces the deviance by the most.
And that ties back to the decision tree that you were talking about before. It
Yeah,
chooses the best one and then makes those decision nodes.
exactly. That's how the decision nodes come into place in the first place. That's how they form. Yeah, that's how the tree forms. But that's CART. So what is random forest? How is random forest different? So what random forest does is, so CART is one single tree. What random forest says is, now let's not use one tree. Okay, let's create 50 trees or 100 trees or 200 trees. And for each of these trees, they create it in a different way. For example, if you're making your machine learning model based on 5,000 records in a data set, the first tree would be a random sample of 300 random trees. The second tree would be based on 300 other random trees. The third tree would be based on a different random subset. And each branch in each tree is based on a random subset of variables. So not every variable is considered for every split of the tree, and not every observation is considered in the construction of each tree.
So, can you reiterate why this randomness is important?
So if you let the tree look at all observations and all variables at the same time, then all the trees are going to be exactly the same, right? Do you get why? Because
Yep.
all the trees are going to split the same multi-dimensional space in the exact same way if you allow it to do so. And we don't want that. There's no point of doing that. The point is, you want 50 different trees to give 50 different predictions for each observation, and then you want to average that prediction. So if it's a regression case, you want to average it. And if it's a classification case, you kind of want to take a majority voting.
And why wouldn't we just try to, have the maximum amount of trees that our compute power allows?
So for every single problem, there's a drop off in the value given by a marginal or additional tree. So in some cases, whether you have 50 trees or 5 million trees, right, it will add 0.001% in predictive accuracy. But the downside to that is a lot. You're using up a lot of compute. So the cost benefit does not make sense in that case.
And how about overfitting? When does that come into play?
Yeah, so this actually, so using different samples and using different variables for branches actually helps reduce overfitting because you're not exposing the entire training data set to all the trees, right? So that actually does help reduce overfitting. But the more trees that you have, it is safe to say that the possibility of overfitting may increase. But again, it's kind of curbed in random forest to a certain degree.
And I know I brought up this new term called overfitting. Maybe you want to give a little bit of a definition of what that means?
Okay, so overfitting basically means you can create algorithms to perfectly. So let's say you have again 3,000 observations in your data set, and these 3,000 observations are past data, so you already know the outcome of these data points, right? So you're basically training your algorithm based on these 3,000 observations, and you can easily train an algorithm, even a cart algorithm, to perfectly split these data points and perfectly predict every single data point in your training set, in the set that you create in your data set that you use to create the model. But when you do this, when you're perfectly creating a model based 100% on just training data, when you show this model to new data that it hasn't seen before, it's not going to know what to do because it's only built on 3,000 data points. So after a point, you're basically fitting in noise. You're not fitting in signals.
So it's just tuned so much to the data set, your training data set, that any new observation, it's not meant for any new observations. It's just
Yeah,
meant for old data. But that's basically useless to most companies.
that's useless. You don't want a model that's really good at predicting yesterday's prices, but is really
Yeah.
bad at predicting tomorrow's prices,
Yeah.
right? Yeah. You
Yep.
want you want that's why data scientists split data sets into training data sets and testing data sets, and they choose models based on how it predicts unseen data. We don't care about how it predicts data that it's already based on. And Addy, these machine learning algorithms that we're talking about, random forests for one, they're really powerful algorithms. So they have the ability to uncover and predict very complex relationships between variables. And I have a question, like, given that they're really powerful, why do you think that there aren't too many companies that use these within their firms?
Yeah, and I kind of pointed to this earlier when I said that the majority of decision making is still being done at from a human driven level, and I think that there's this tendency to shy away from machine learning because there's so much misinformation out there, right? And many times machine learning is associated with these complicated artificial intelligence, like robots, natural language processing, and many business enterprise executives don't think that it's applicable to their business. But the machine learning that we're talking about, it relates to predictions, recommendations, insights, things that can be used for every single business unit in almost every single industry.
Mm-hmm.
And I think it's more so bringing machine learning to these basic problems. It's
Yeah.
not all about high level artificial intelligence Watson. It's about using machine learning in everyday instances, and I think companies are starting to recognize the value. In 2020, 58% of executives say that they've already started implementing machine learning projects in their companies,
Oh, really?
and yeah, and that
Wow.
there's an impact to this too. Like machine learning algorithms actually bring an increase, can bring it up to a 40% increase in productivity and a 38% increase in profits in companies that decide to implement machine
Mm-hmm.
learning.
So, what do you think the harm is? Do you think is there a quantifiable number in terms of dollars of what companies would not like? What's the harm of not implementing machine learning?
Yeah, that's the danger, right? Well, what's going to happen if you don't implement machine learning if your competitors do? And
Hmm.
there is a tangible financial harm. In the year 2020 that we're in right now, experts say that 1.2 trillion dollars is being taken away from companies who are not using machine learning uh,
Hmm.
by companies who are using machine learning. So there is a risk associated with not, being ahead of the game here and implementing machine learning. So Ryan, I mentioned before how this type of machine learning that we're talking about is used for day-to-day, problems. So could you give some examples on how, day-to-day activities can be helped by machine learning?
Okay, that's a good question. I think wherever you can make a prediction in a company, that's where you can use predictive machine learning. But if you want specific examples, there are three that come to mind. The first is predictive maintenance. So when I say predictive maintenance, what I mean is that companies that have machinery, so we're looking at manufacturing companies, right? Machinery after a point break down and you have to perform maintenance on it. So, what predictive maintenance does is instead of being reactive, and by reactive, I mean fixing the machine or maintaining the machine when it breaks down, we want to be proactive. We want to predict when these machinery are about to break down so we can prevent them from breaking down. And this actually costs much less because when it breaks down, you have to A, pay for fixing the machine, and B, you don't have output during that period where where it's being maintained. So what predictive maintenance does is it takes sensor data or IoT data, and based on patterns that it has seen in the past, these algorithms predict when they think that the machine is very likely to break down. And so during those periods, you can give it rest. You can switch it off for a couple hours or whatever. There could be millions of things that you could do to it. That's the first. The second is more of a marketing slash sales example, and this is churn. So this is also very specific. It's a huge problem in telecommunications companies. So churn is when a customer leaves your company, right? And you want to focus your promotional and advertisement efforts on those customers that are more likely to leave your company versus those customers who are not likely to leave your company. So what these algorithms do, these churn algorithms, is they predict which customers are likely to leave the company because of customer behavioral metrics, maybe demographic metrics, maybe psychological metrics. It could be a bunch of different metrics. So you can focus your efforts on these customers. And the third that I was going to talk about is quality testing. So when I say quality testing, what I mean is think of a production line. Okay, there's a product that goes from the start of the production line to the end of the production line, and at the end of the production line, there's often quality testing, and more often than not, companies have have all of their products go through the quality testing portion. But what if we can introduce a machine learning algorithm that looks at all of the products, looks at all of like features of different products, and categorizes them into two buckets. One bucket is products, specific individual products that are more likely to be defective, and specific individual products that are less likely to be defective. So now we can perform quality testing on only that group of highly susceptible to defects group of products. So now you can cut down human hours spent on quality testing, and you can cut down costs spent on quality testing. So overall, gives you much more value and much higher returns.
And it's important to note that all three of these are really issues that any manufacturing company will have to deal with, especially the predictive maintenance and quality testing. Right? And
Exactly.
it's not just the Teslas of the world. Every manufacturing company has to deal with this. So that means any manufacturing company can implement machine learning.
Exactly. So this goes back to your point too. This is not driverless cars. This is not robots carrying stuff around. This is this is very very applicable to most companies in the world.
Yeah, and I have a great example of a real life use case of this is GE engines. We
Okay.
have we have the GE engines on these huge airplanes. And like you said with predictive maintenance, GE is actually using machine learning to tell the aircraft engineers at these airports when their engines need maintenance. So there isn't a time where the engine will fail and the whole aircraft is on the ground unable to fly, because that's a lot of money for
Exactly.
these
Yeah.
companies. So GE is doing a great job, and there's hundreds and hundreds of examples of this, but I just thought that was one that was really applicable to manufacturing. So, this was a great conversation that we had today, kind of giving an introduction into machine learning. We talked a little bit about random forest and CART and the specific algorithms. Then we went into the statistics about how machine learning can increase productivity, can increase profit, and then talked a little bit about the risks of not doing machine learning and how the companies who are implementing machine learning are siphoning off money from companies that aren't. And finally, we ended with a couple of examples that manufacturing companies or any company can implement in their day-to-day processes. Do you have any last thoughts on our conversation here today, Ryan?
No, I think it was a really productive conversation, and it's the biggest takeaway that I would say is just to understand that machine learning, and I know we said this a lot of times, but machine learning is not the scary, complicated, and very difficult to apply concept. It's a straightforward concept. It's a very applicable concept. It's something that every company should have. And really,
and like I said, it's not any new infrastructure, right? For the most part, it's infrastructure it's infrastructure and data that these companies are already compiling. So it's just really using what these companies are already doing.
Absolutely, yeah.
So that kind of concludes today's discussion. But I'm excited next week to talk about how Uber specifically has been able to implement machine learning in all facets of their company. So that's going to be a great discussion next week. So thank you, Ryan, for being here, and thank you all for listening in. And we look forward to next week.
Thank you for having me, Adi. Thank you, everybody.